Hey, physical science kids, Mr. Tima here. I'm going to talk to you about your waves part 2 notes, which is about refraction, diffraction, and reflection. I'm going to try to go back and forth here, and we're going to show you some visuals and stuff like that. But first one is refraction. Okay, has anybody seen this before? Like when you look at a cup of water and you're like, wait a minute, my straw's bent, my straw's broken, whatever. Okay, something like that. Or maybe, you have this thing, like if you're sitting in water, if you've ever gotten down there, it kind of looks like if you put goggles on, the body of somebody is not attached to their head, or physics is fun, if you will. And it looks like he's decapitated as well. All right. Perhaps you've looked and seen light like this coming down. Like if you go to the Columbus Zoo and you go down there where the polar bears are and you go underneath, you'll see this all the time. Or they have that new aquarium section with the natural sunlight. This is all refraction. Okay. And what refraction is the bending of light into a medium. Okay. Literally, the waves come in and they bend into a medium. Okay, so a good way to look at that, I have a little simulation here for you, is if we pretend it's a wave, all right, we pretend it's a wave and we look right here, these waves are bending into the medium. It should go straight, but it doesn't. It actually bends in. Okay, we can even make this more extreme. If we go like this, and if we go straight on, right? If we go straight on, it won't even let me go completely straight. It wouldn't go anywhere. But you notice more of it is bending into the medium. Okay, we'll come back up here and get that nice little bend. So here's our little wave light. All right, what if the material down, this is air up here and this is water, if you can see that. All right, but what if it was more dense? What if this was more dense? Well, it's actually going to bend, what do you think? Less or more? Would it bend less or more? Well, if it gets more dense, you'll notice it bends more. Okay. If I make it the same as air, it's straight. Look at that. It's exactly the same. It's like just a beam of light shining through there. But as that bottom one gets more dense, we're going to bend more and more into it. Okay. It's kind of crazy to think about. All right. What's really cool is it doesn't matter if it's actual waves or if it's literally a laser light, the same principles hold true. If it's the same, it's straight on. If it's more dense, it's going to refract more. All right. I'm going to reset this because we're going to come back to this here in a little bit. So back to our little presentation here. Again, the waves are going to come in and they're going to bend into the medium. And depending on the density of that medium, it's going to become more or less of a bend. All right, here's just another quick picture. Again, kind of showed you there. It may not, it's going to bend at the same everywhere depending upon this medium. It's all going to be the same bend. It just might take longer to bend some more, just how long it takes to get to that glass. This is why when you look at the moon, sometimes we call it a blue moon, we call it a red moon, all that kind of stuff is because the sun, the light from the sun at night is refracting around and causing the moon to look like it's a different color. Maybe you've seen that. It's called a blood moon, stuff like that. This is also why if you go fishing and you try to stab a fish, it may look like your spear is broken. All right, anything like that. One thing is, think about it. The image is being refracted. All right. So when we see this fish, if we throw this spear at this fish where we see it, we'll never hit it. Okay. Because that's really where the fish is. But when we look, think about it. Our vision, when we look, we see that image and it's going to refract the image to put like a fake fish right here. Okay. When we look from up above, it's going to look like the fish is right here. So if you threw that spear where you see that fish, you're going to miss. It's going to go in front. So if you ever found yourself in the wilderness and had to kill a fish with a spear or grab one, you always want to, this is where we think it is. We always have to grab behind where the image is. So if we see a fish in the water here, that fish is really back behind where we see it because that light has been refracted in. All right, diffraction. All right, diffraction is the bending of waves around a barrier. Okay, so for example, if we look here, this would just be a regular old wave with no barrier. Pretend this is the shoreline and this is the ocean. We don't really think that it ever ends. It looks infinite, okay? All right, we can speed up the frequency. All right, we can speed up the frequency and have more waves crashing, but nothing changes. This is actual water waves. All right, what if it was a sound wave? What if it was a sound wave with no barrier? Okay, we'll send out a sound wave. It's the same thing. Okay, nothing changes. What if it's a laser light with no barrier? Again, it is the exact same thing. There is no difference between a physical water wave, sound wave, and a laser light wave. It doesn't matter. They're all the same. But let's go back to water. Okay, now let's add one slit. Okay, if you notice, it's going to diffract. Okay, it's going to bend around the medium. It's going to bend. It doesn't go straight through. Well, what if we make that? What if the slit gets bigger? What if we make it bigger? Okay. Well, it kind of doesn't round off as much because some of it can kind of go through without being interrupted. Okay. If you were on like a kayak or something, you could almost go straight through there. As you get here, it kind of gets diffracted. Well, the opposite is true as well. As the slit gets smaller, there's more diffraction. All right. There's more diffraction, but it doesn't matter. If we go back to sound and we put one slit in, same thing's going to happen. That sound is going to bend around that medium. Laser light, same thing. We'll go to one slit with the laser light. Same thing. That's a little bit more detailed. I like how that green's on there. Okay. And again, as the slit gets bigger, more intensity gets through. It doesn't bend as much. The smaller that slit is, the more diffraction we have. Okay. All right. We'll come back to this here in a second. All right. You should have watched this video. You should have watched this video of Dr. Quantum. That was part of your notes. So make sure you watch that if you hadn't. He's going to take you through the famous double slit experiment. But basically, that's why it's hard for you to hear radios and stuff when you're in big cities, or if you're in a parking garage or something, because this sound is being sent out. It's got to diffract around these hills. Well, what happens is when it diffracts, it doesn't quite get to where it needs to go, and we get these dead spots. Okay, we get dead spots or places it's shielded, and you know that when you've listened to a radio in a car or something like that. Where's the best place to sit at a concert? Well, after you've watched the Dr. Quantum video, we're going to go here. Let's just pretend it's sound like it normally is. And now we're going to go to a double slit. Okay, so here we go. Double slit. All right. The white parts are the most intense parts. Okay. The dark parts are where you have um, the least intense parts are there. Let's turn up the frequency here. Let's make it kind of come in there a little faster. All right. So let's pretend you have basically some smaller slits because, speakers are pretty small. Okay. All right. So where is the best place to sit for a concert? A lot of people will want to sit in the front row, but if you notice, there's a lot of black in there. There's a lot of kind of covered up areas. Out here to the side, it's not very, clear, because what happens is you kind of get this kind of muffled or not clear. Actually, the best places to sit at a concert are actually right next to the aisles. If you have a center section and two side sections, those next to the aisles are actually, if you notice, is the most intense and kind of clear sound. Anywhere in this kind of funnel, but mostly right there and in the back. In the back's always really good, which sounds crazy because those are your cheapest seats. But if you're there for the music and not really just to, see how close you can get to the performer, that's why it is. All right, reflection. You guys are the most familiar with reflection. All right, reflection, looking in the mirror. Sometimes you've probably seen how crystal clear lakes can be, and you get these really cool images and things like that. All right, this is hugely important though. There's the angle of incidence, all right, and the angle of reflection. And that word incident, it is the angle in. It is the part that's coming in. All right. The angle of reflection is that part that reflects out. So I always like to think angle of incident, angle of reflection, the rebound. Okay. So angle in, angle rebounding. Okay, this is why things have shadows. If you take Mr. Shaw's class, Mrs. Armstrong, anything like that at school, you'll see that there's this reflection. Okay, and what happens is that's what causes shadows because light comes in and bounces in all directions off that angle. Here's something very important about the angle of incident and the angle of reflection. They are always equal to each other. Okay, they are always equal to each other. I'll show you here, kind of prove it to you since I know you guys don't believe me. All right, oop, I gotta go to my pointer. Sorry about that. All right, so right there. Okay, so let's go to a laser light. Let's go to a laser light. This right here is the angle of incident. This is the angle of reflection. Well, let me get this protractor out here. If we put that there, it's a lot easier to see that. Let's try to line that up as best I. Oh, come on, computer. All right, we'll get that right there. 0 right there. Okay, so right now, let's make it simple. The angle in would be 30 degrees. We notice the angle out is 30 degrees. Okay, we're kind of ignoring this bottom line. That's the refraction. We're only looking at the reflection right here. Okay, now, and some of you maybe played with like a little laser for your cat or something, and you may have done it on a mirror and noticed this before. But as I start increasing my angle of incident, notice my angle of reflection also is increasing. And if you notice those numbers, 60, 60, 70, 70, 80, 80, 90 would be perfectly 90. And notice there's no refraction anymore because you can't have refraction unless you're bending into a medium. I will go wave here. Same thing. It doesn't matter. It's the same idea. No matter what, those waves are equal to each other. Look at that. At 0 degrees, it's a perfectly straight line. If it's a ray with its reflecting, it's going to come straight back on there. All right. And it doesn't matter because we're not talking about refraction. We're talking about reflection. Okay. Well, hopefully you've enjoyed these notes. Okay. We'll move on to a different topic next time. But hopefully you enjoyed. This is refraction, diffraction, and reflection. Angle of incident equals the angle of reflection. All right. We'll talk to you next time. Mr. Tima out.